Okay, we have for today another integral from the MIT Integration Bee 2006. This one is 22. We have the integral from 0 to 4, 3 to the square root of 2x plus 1 dx. Okay, I thought this was pretty interesting. Just because we've got a couple problems here. First of all, we don't like the base to be 3 in the integral, so that's the first problem. But then also, we don't really like the exponent to be square root of 2x plus 1. So I think what I'm going to do first is just deal with this square root and the exponent. So what I'm going to do is do a u substitution for that. So we'll come over here and we'll set our u equal to 2x plus 1. So first what I can do is square both sides. So we'll have u squared equal to just 2x plus 1. Subtract 1 on both sides, and I'll rearrange. I'll put this as we'll have 2x equal to u squared minus 1, just swapping the order. Divide by 2, and that's going to give me my value for x equal to u squared minus 1 over 2. And what I think I'll do to just clean this up is I'll write this as x equal to 1/2 u squared minus 1/2. So now we can just go ahead and we'll take a derivative to get our dx values. So doing this, we're going to have dx. Derivative here is going to give me just u du. And then I'll just go ahead and substitute. So first, let's update our bounds. So we plug in 4 here. 2 times 4 is 8 plus 1, 9. Square root of 9 is going to give me 3 for the upper bound. Plugging in 0, we get a 1. Square root of 1 is just 1. Then for the integral, this is just going to turn into 3 to the u. And then dx is going to be just u du. But now that we have this broken into like 2 separate functions, what I want to do on this is use integration by parts. We'll do the di method over here to the right. So first we'll have a column to differentiate and a column to integrate. And let's just differentiate u and integrate 3 to the u. Now integrating u, that's just going to be easy. We'll integrate that to 1, and then integrating again, we're going to have 0. But now for the integral of 3 to the u, we could just use a formula for that, but let's just do it out really quick over here. But what I'm going to do is actually do the general form when we have something where we have a constant base that's not e. We can write this as au du. And then we use the formula here we can write for a, we can write this as e ln a. So when we put this together and we transform it over here, we can rewrite this integral as e ln a u du. But now in this form, we know how to deal with this because ln a is just some constant value. So when we integrate this, we just get back the same thing. We get e ln a times u, but then we need to bring this out in the denominator as ln a. But then what we do is we just do this same trick in reverse and put it back in this form, just because we like to see it that way. So what we can do is write this back as au over ln a. So coming back to our table, we can use this formula, but we just have here where our a value is going to be equal to 3. So this is going to become 3 to the u over ln 3. And then we do it again. You can kind of factor out if you want. You could factor the ln 3 in front, and then you get the exact same problem, 3u over ln 3, same solution as we have here. So now we can just copy down our solution here on the diagonals. We don't have to worry about the last row because we have a 0 there. That's going to zero out that last integral. And we have in common this 3u ln 3 in both terms. So what I'll do is factor that in front. So I'll write this as 3u ln 3. Then for the first term, we're just going to have a u. Then we have this minus sign. And then what's left here, because we already used this, we just have this 1 ln 3. And for this, we just need to evaluate it from 1 to 3. So first, let's evaluate it 3. 3 to the 3 is going to give me 27 over ln 3 here. Here we're going to have just 3 minus ln 3. So plugging in 1 here, we're going to have just 3 over ln 3. Then plugging in 1 here, we're just going to have 1 minus 1 over ln 3. Okay, so now I just need to distribute everything in order to finish this off. So for this first term, 3 times 27, we have 81 over ln 3. Distributing in this second term, we get minus 27 over ln 3 all squared. Here we're just going to have minus 3 ln 3 multiplying by this 1. Then here minus 3 times minus 3 gives me plus 3 over ln 3 all squared. Combining these two terms here and subtracting, we're going to have 78 over ln 3. And then combining these two terms, 3 minus 27 gives me minus 24 over ln 3 all squared. And that's it. Okay, so there you have it. Pretty good problem from MIT 2006. Thanks everyone for watching. Have a good day.